Hello and welcome to Numeristical. We are continuing our series on Major League Baseball game prediction. We are now in the 14th video of the series. In the last couple of videos, we built a model that predicts the distribution of the number of runs scored for a team, given that team's hitting statistics and the opposing team's pitching statistics. And then we took the combined predictions for each game. So we predicted the number of runs scored of one team, predicted the number of runs scored of the other team, applied an independent assumption to get a distribution on the total number of runs scored in that game, and used that to make predictions about the over-under. And we got some pretty good results, and some results that seem to be beating the Las Vegas bookies and beating them by enough to actually make some profit. Now in this video, we're gonna dive a little bit deeper into the model and specifically check some of the calibration of the pieces of this model. So one issue that came up was that while the model was still good at making predictions, they were making useful predictions, it was more confident than it should have been in its predictions. So it thought it was going to be right like 70% of the time and actually was right, only 57% of the time. So we're going to start diving into trying to diagnose why that's occurring and see if we could address it and thereby improve the model. So that's what we'll be exploring in this video. Before we go to the notebook though, I'd like to ask you again if you could please like the video and subscribe to the channel. It really helps me out a lot if you could do that. I also want to encourage people to join our private Discord channel. We've had some pretty good activity on that. And if you'd like to engage further and ask some more detailed questions and generally discuss this, it's a great place to get involved. So I'll put another invite link in the description of the video. It'll be good for 7 days. And if you're watching after that and want to join, please just ping me directly and I'll see what I can do. And with that said, let's cut over to the notebook. Okay, so in this notebook, we're going to examine the calibration of the run scored model. Now, in the last couple of notebooks, as I described, we built the model to predict the distribution of runs scored for an individual hitting team versus a pitching team. And then we used an independent assumption to predict the probability for the total number of runs scored and thereby determine whether you were over or under the line for that game. And the model looked like it was profitable, but these final predictions of the model were clearly not well calibrated. So, for example, when we were analyzing the betting and how profitable we would expect this to be, we said, hey, there was 362 games, and if we bet on those games, we'd be right 57% of the time, and that was enough to make money. But if you look at the probabilities that our model spit out, it really expected to be right more than 70% of the time. That was the threshold that we had set to get to those 362 games. So we thought, the model said, hey, we should be right 70% of the time, ignoring pushes. But actually, we're only right 57.2% of the time when you ignore pushes. So what could be accounting for this error? Well, there's two main possible sources for this error. One is that the run score distribution is off somehow. It's not well calibrated when we say there's a 14% chance that the team will score exactly 2 runs, that probability is not quite accurate enough in practice. The second possible source of the error is that this independence assumption is very flawed. So the problem being, yes, marginally, when we say this team's 14% chance to score 2 runs, it's true. And this other team, when we say it's 15% chance to score 3 runs, that's true. But they're dependent. So whether or not this team scored exactly 2 runs actually affects the other team's score. And we know that this independence assumption probably is flawed in practice because we know teams make strategical moves based on the status of the game. We know that if it's a close game, they're going to try really hard to score 1 run and be less likely to go for a big inning. We know if they have a big lead, they will probably not use their best relief pitchers, especially if they're tired. And so that might give the other team a chance to score. There's also potentially other psychological factors, morale. If you're down by a lot of runs, maybe you give up and you stop trying. It's hard to know what's really playing out. And we'll be able to explore that a little bit as we move forward. But both of these potential flaws could clearly be accounting for the lack of calibration in the final model. So in this notebook, we're gonna look at the run score model and try to get a sense of how well calibrated is it, to what degree do we think that the problem lies with the run score model versus the independence assumption, and then we'll decide what to do next from there. So to outline a few things, first, to get a sense of how poorly calibrated this overall model was, let's do a little bit of basic statistics. So there were 362 games. We ignored pushes, so that's why they don't quite add up. But of the other 197 plus 147 games that weren't pushes, we were right 197 times, wrong 147 times. But our model had chosen a threshold where it said I should be right more than 70% of the time. So to show how unusual that is, let's simulate flipping a coin this many times, 197 plus 147, so that's 344. So we're going to flip 344 coins with a probability of 0.7 of being heads. And we're going to repeat this 100,000 times and see how likely is it that we would only get 197 heads if the probability is really 70%. And if you look, you can see that the 197 is very, very unlikely. Out of 100,000 trials, I don't know if it happened at all, or maybe it happened once, but this is a very, very unlikely outcome. If the probability was truly 70%, it would be very, very unlikely. So this is not bad luck. This is that our model is overstating the probability of us being right. It's pretty clear that the model is not calibrated, at least at that extreme. So I want to go through and just first recreate the model. So I just rebuilt the same model as before with the same features, just reran everything here, and it's still finishing up. Okay, so the model finished running, and now we're going to start examining the calibration of the run scored model. So we want to know our model. It makes these predictions. It says number of runs for this team is going to be 0 with a certain probability, 1 with a certain probability, 2 with a certain probability, and so forth, up to 16 or more. So we want to know, for example, when it predicts that the probability of scoring exactly 1 run is probability 0.15, does that really happen 15% of the time? Or are we off somehow? Are there any sort of systematic biases in this run scored model? Now, we've got effectively a 17-class model. So that makes predicting or evaluating calibration a little more tricky than when you have just a binary model. So to get at this, we're gonna approach calibration and evaluating the calibration in 2 different ways. So the first way is we're going to look at each multi-class prediction, and we're going to think about those as 17 different predictions. So the model says, I think there's a 10% chance of 0, a 12% chance of 1, a 15% chance of 2, and so forth. We're going to say, okay, 0 had a certain probability, 1 had a certain probability, 2 had a certain probability. We'll treat those each as 17 different predictions. Now, the challenge here, though, is that exactly one of those 17 is going to be right. So those 17 are not actually independent observations. And we'll show how to address that in a second. The second way to evaluate calibration is to look at each class as a different binary classification problem. So we've got all the predictions about whether it was a shutout or not. So we could say 0 runs versus not 0 runs. Let's see, is the 0 runs part calibrated? And likewise for 1, for 2, for 3, for 4, and so forth. So let's start with approach 1, and as I said, there's a slight issue that we don't have independence between the different observations in each row. So as a first attempt to address this, to make sure we're on a little bit safer mathematical ground, we're going to, in each row, for each game, we're going to randomly sample one of the columns to be the one we're going to evaluate for that particular row. So what do I mean? Let's get into details of what I mean. So the first thing I want to do though is create what's called a one-hot encoded version of y-test. And this just means, so y-test itself is a number between 0 and 16, right? That represents the number of runs scored. 16 represents 16 or more. Now, we're going to represent this by what's called a one-hot encoded matrix. That basically means when I see a 7, and remember this is a Pythonic 7, so we're starting counting at 0, I'm going to put a 1 in the 0, 1, 2, 3, 4, 5, 6, 7th column. Again, Python 7th column. When I see a 4, I'm going to put a 1 in the 4th column. When I see a 5, I'm going to put a 1 in the 5th column, and so forth. And this is just a convenient framework that will make the data manipulation a little bit easier. And likewise, I'm going to take my predicted probability distributions and put them all in a matrix. So this says for the first data point, here are what the model predicted for each of the probabilities. This is the probability it thought of a shutout, about 5%, exactly 1 run scored, thought about 10%, 2 runs scored, about 13%, and so forth. Here's the predictions it made for all of these 17 different outcomes. And if you add up all these numbers, they'll all add up to 1 for each row. So to get this sort of collection of predictions and results that I then want to see how well calibrated it is, I'm going to randomly sample an index in each row. So I'm going to do that here. For each of the y-test rows, length of y-test rows, I'm going to pick a random column, and then I'm going to look at the result of that column, and I'm going to look at the probability associated with that result. So if I run this, you'll see, so in the first row, I randomly picked column 12 to use as the one. For the second column, I randomly picked 15. For the third column, I randomly picked 0. And here are the probabilities. So for the first row, I picked 12, so that's this one here. For the second row, I picked 15, that's the next to last one, that's here. And for the third one, I picked 0, so that's the first one here. And in all of these cases, the outcome did not happen. But so now what do I have? I've got a bunch of probabilities and a bunch of binary results. And I want to assess how well calibrated these numbers are. There's a bunch of predictions I made. They're all independent because I only picked one thing out of each row. So in the first game, I made some prediction. I said, and it's a binary prediction. I said there's a certain probability. The run scored, I decided to bet on 12. The run scored being 12. I said, here's the probability, and here's what happened. Second game, I decided to bet on the run scored being exactly 15. Here's the probability. Here's what happened. The third game, I decided to bet on a shutout. Here was the probability my model gave. Here is the result. So now we're going to look at this entire collection of predictions and results and assess how well calibrated my prediction mechanism was. So I'm going to do a reliability diagram, and here's what we get. So when you're looking at it, you see most of these things are in the error bars. We've got one over here that's outside, so that might be worth sort of digging into. And we've got one over here that we can't see that well, so I'm going to zoom in actually. I'm going to zoom in on this lower left part of the graph to try to see that a little better. So that one down there, you see it's really right on the edge of what we would expect. So it's possible that we're under-predicting this probability. And this is a low probability event. So we're saying, the model is saying the probability should be around, looks like 0.008 or so. And it looks like it happened about 1% of the time. Now let's look at the right half of the graph a little more closely. And here we see this was a problematic one. We predicted about 17%. So when we made predictions around 17%, they only happened around 11% of the time. Again, in this sample of data. So remember, I'm only sampling one outcome per column, and I've got about 16,000 columns, so I've got a decently sized set, but not like really a huge set. But there seems to be a little bit of evidence that the small probabilities were under predicting on some of the small probabilities and maybe over predicting on some of the large probabilities. The thing is, if I change this random seed, so let's change the random seed for a second. I'm going to make this 1 now, so I'm going to resample. So now I'm picking a different set of indices here, and let's regenerate my reliability diagram. You see, we kind of get a different story. Let's see. Yeah, so here I don't see that same under prediction here. This one it looks fine. In fact, I get over here. This one seems to be a bit under predicted. Here we're kind of seeing the same thing. So maybe that suggests that's a little more stable. Let me look at another one. Let me let the random seed be 2 and see what happens there. So this time that one looks fine. And these all look fine. Actually, this one over here seems to be a little bit off. Let me go back up here. Yeah, I've got one over here that seems a little bad. So again, this is hard to tell. We're not seeing anything super conclusive. And part of the problem is that we probably just don't have enough data, especially as we're doing this sampling technique to ensure our independence. So next, let's take the second approach, where we do class by class, examine the calibration. So when I predict exactly 0 or not 0, 1 or not 1, 2 or not 2, let's look at the calibration here. And so I'm going to do them in groups of 4, just to run through the 17 a little bit more quicker. So the first set of 4 plots is going to be for the first 4 classes, so 0, 1, 2, or 3. So let's look at the 0, 1 first, and you notice that we've got 1 point over here that's out of the error bar. And then you also notice the next 4 are also, we seem to be over predicting the true probability, or at least the empirical probability. So when I look at these diagrams, I also look for, if you see several bars in a row that err in the same direction, and some of them are over or near the bounds of the error bar, that starts sort of becoming stronger evidence that there's something miscalibrated. So, because it's very unlikely, first of all, that you would have 5 errors in a row in the same direction, and this one by itself seems to be statistically significant. This one's right on the edge, and the other 3 are, somewhat. So when I see this, I start to think, maybe something's going on here. Maybe I'm over predicting the probability of a shutout, at least in this test set. Now let's look at when I predict for 1 run scored. And again, I see a fair amount of over prediction. The empirical results are coming in lower, below this y equals x line. And let's look at 2 and 3. And again, we have a lot lower here. And this somewhat, but if you look at the totality of these 4 plots, right, there's a lot more cases where we're over predicting, where the empirical dots are coming in below the line, than there are above the line, right? This one is above the line. But we've got a lot below the line. So this is starting to suggest that for the low numbers of runs scored, we're over predicting the probability of kind of low scoring games for a particular team. Again, this is just kind of a holistic. We want to sort of gather evidence from a bunch of different ways and kind of see if there's a totality of evidence that suggests something. We don't want to overreact to one plot or one piece of evidence. Now we're going to look at 4, 5, 6, and 7. Let's see, for 4, you got this one below, right on the edge. The others within the error bars. This one's kind of close to the edge. This one seems to be, systematically, we're under-predicting the true probability. So now we're starting to see something different over here. But again, well, I guess one of these is outside there. For 6, this seems to be all within the error bars. This seems to be pretty well calibrated. 6. At 7, we've got 1 under prediction here. Let's look at 8 through 12 now. 8, everything's within the error bars. This seems okay. 9, we've got 1 that we're under predicting. Everything else seems pretty good. Now 10, we're starting to see a little more under prediction. We've got this one that's out of the error bar, this one right on the error bar. This one's pretty close to the edge of the error bar also. And now for 11, we've got a pretty big under prediction here. Going down further to 12, 12 seems mostly okay. 13, again, we're getting some under prediction. 14, got another one under predicted, and this one is close. 15 seems mostly okay. 16, we've got another under prediction. So it seems like, if you look at like 10 through 16, we've got several that are at or near that suggest under prediction, and nothing that really suggests over prediction. So if I had to summarize this, I'd say that there's also some evidence that we're under predicting the probability of high scores. So if I'm looking for something where I think there might be a problem with the model, I'd say it might be the case that we're over predicting low scores and under predicting high scores. And again, what makes this consistent? Part of what makes this consistent is that I saw a similar pattern in 0, 1, 2, 3, 4, right? And no one of those looked particularly strong, but the fact that you had sort of 5 numbers in a row that were all at the low end of the spectrum that kind of showed the evidence pointing in the same direction, and then conversely on the other end of the spectrum, for the high scores, we saw a few in a row that seemed to be pointing in the opposite direction. So in totality, this seems to suggest to me that there might be some miscalibration. So let's look at, to do another sort of check on this, what I'm going to do is I'm going to say, overall, if you average all the predictions I made, what's the average number of 0, 1, 2, 3, and so forth my model would have predicted? And then let's compare that to what really happened. So my model's predicted, on average, if you play out all its predictions, you should have had 6.5% shutouts, 11.2% one-run games, 13.8% two-run games, and so forth. Here's what really happened. There were 6.1% shutouts, 10% one-run games, and so forth. Let's take the ratio of this one over this one. So if the number is bigger than 1, it means we overpredicted. The number is less than 1 means we underpredicted. And you can see the first 5 numbers were all overpredicted. And then all the rest were underpredicted, with it really sort of getting big over here, right? Because this one was really right on target. And again, these were in the 90s. This is not so far off, but now below here, most of them are below 0.9. And again, I'm just kind of using heuristics here. But there seems to be something going on where certainly in this test set, the model overpredicted the probability of 4 runs or less, and it underpredicted the probability of 10 runs or more. So what could be accounting for this? The most likely possibility that I would, again, guess at this point of the analysis is that, that there's what's called model drift, right? Which means baseball changes over time. And we know this very well, right? If you saw in the 90s, kind of during the steroid era, there were a lot more home runs, the scores went up. Things change over time. There were dead ball eras. As the game changes, the amount of scoring adjusts. So, this violates one of the key assumptions of all of this modeling, right? The key assumption of this modeling is you've got this data generating mechanism, and it generates this data, and it's constant over time. But reality usually doesn't play out like that. Reality says, hey, this model's sort of changing over time. So we have to always adjust our approach to fit the reality, and not just say, I'm going to close my eyes to the things that violate the theory and just pretend they're not there. So as a last sort of analysis, I'm going to do a reliability diagram of the full one-hot matrix. So remember, before I sampled one column from each row so that we would have a bunch of independent predictions. So now if I just used all of them and ignored the fact that within each row I've got a lack of independence because it's guaranteed that each row will have one thing correct and 16 things incorrect. And you could spend a lot of time really trying to play out in your head what are the implications of this. I do not claim to have totally solved that, or even to have solved it at all. But there's an argument to be made that what this would probably do is sort of reduce the variance of your bars, because you're guaranteed to have one success out of every 17 predictions. So that sort of lowers the variation a little bit somewhat. And this is a very hand-wavy argument. So take that for whatever it's worth. Let's just look at it, kind of see what happens, and take it for whatever it's worth. So this is using all these things. Now I'm cheating a little bit because these things are not independent. So the error bars, for example, which assume that everything is independent, have to be sort of taken with a grain of salt because these observations are not independent, and so forth. But here's what we get for the reliability diagram. And again, let's zoom in. Zoom in on the lower left. So the lower left, what this is saying is that small probabilities are being underpredicted. And if you dive into the numbers, you'll see that these small probabilities correspond to big scores. Because if you look at the shutout, right, from 0 to 5, you generally have pretty high probabilities, right? Shutouts usually range from 5 to 10%. So these numbers where we're predicting like 1%, 3%, these are all when we're predicting big run totals. So again, what this reliability diagram says now, with again, it's a bigger sample size that has this sort of weird bias in that they're not fully independent observations. But this is saying that I'm under predicting the low probability events, and that another way of saying that is that I'm under predicting the probability of high scores. And let's look at the right hand side of the graph. And here we see again, if you look at kind of these three middle bars, we've got 3 in a row that are outside the error bar. And these correspond to probabilities between 13, between like 12 and 18%. And so these are the high probability events. These are the, kind of from 0 or 1 to 4. So this is another bit of evidence to suggest that we're over predicting. With respect to this test set, we are over predicting the probability of low scoring games and under predicting probability of high scoring games. So again, the totality of this suggests that, yeah, in our test set period, we're kind of making there's some sort of systematic bias in our model versus the reality. Let's take a look at what's the magnitude of these errors though, because I don't think the magnitude of these errors really explain the degree to which we had the problem of miscalibration of the overall model. So if I look at 10 or greater, my model predicted this should have happened in 6.6% of the games, and it happened in 7.9% of the games. So that's statistically significant. Again, loosely speaking, there's probably enough evidence here to say, hey, there's a problem. Like, you're not well calibrated. But in terms of the effect on the model, that shouldn't really account for being off, having a set of observations I think should happen 70+% of the time and only happen 57% of the time, right? Because this is only a 1.3% change. And likewise, if I look at the 4 or less, the model said this should have happened 4 or less should have happened 46% of the time, actually happened 43% of the time. Again, it's probably off, but this 1.3% in one direction and 3% in the other direction can't add up to like the 15% discrepancy we're seeing in that overall model. So let's just do one last thing. I'm going to create some variables for just was the number of runs less than or equal to 4 versus number of runs greater than or equal to 10 in that runs data set. And I'm going to look at it by season to see how this changes over season by season. And I'm going to plot the mean in our training period to kind of see, does the test period look different from the training period? So here's for low run games. So here's the percentage of games where a team scored 4 runs or less. So each game kind of is two trials. Team A, did they score 4 runs or less? Team B, did they score 4 runs or less? Our test period is the last 4 data points. It's 2019 through 2022. So can't really say, it seems to be really right around the mean. 2022 was bigger, 2021 was right at the mean, 2020 was a little lower, and 2019 was a little lower. But again, this does not show me that, hey, the test period was out of whack overall. But one thing to notice is that this hops around a lot, right? So it's been as high as, in any particular year, it's been as high as 62% and as low as 49%. So when we look at our model said it was 46% and it was actually 43%, that doesn't, and actually this is off. I should make this :5 to make it comparable to what the other one was because I want 4 or less. So 59% versus 55.8%. So again, like a 3% difference. The model says it should be around 59% and it actually came in around 56%. Given how much this changes from season to season, it doesn't really give me too much pause that, oh, we did something dramatically wrong, because this thing varies a lot. Likewise, let's look at high runs by season. And again, the same thing. So again, our test period, again, can't really say it's like dramatically off from the average. But again, we see a very big difference. This goes down as low as below 5% and as high as almost 12% season by season. So when the model said it was 6.6% and it actually ended up being 7.9%, again, not going to beat up on the model too much for being off by that amount, given this huge amount of variation. Okay, so what do I take away from this as we wrap up this video? We've got some evidence that our model, at least in the test set period, is over predicting the probability of lower scores, under predicting the probability of higher scores. Now we could try to calibrate this, and I'll talk about this going forward. We could sort of try to do a calibration, but given what we've seen, I'm not sure calibration is going to help much, because this varies so much season to season. And if you calibrate, you're basically sort of picking one point on this graph, saying, I'm going to calibrate to this, and that's going to be the answer going forward. Now, when would calibration be sort of an easier choice? If this was very low, and then it jumped up, and then it remained pretty high, I'd say, okay, something changed in the past. And we were in this regime over here, and now we're in this regime over here, and I want to calibrate to the regime that we're in now. That's where you'd expect calibration to really have a clear win. But in this, where we're sort of migrating all over the place, it's kind of hard to say whether calibration will help. See, like if we stopped history at like 2007, you might say something like, okay, see, we had fewer runs before in the 80s and early 90s, but now we've jumped to this regime of higher scoring. And so I want to calibrate over here so that I can predict over here better. That would be sort of a clear win for calibration. But here where it's sort of jumping all over the place, we don't really know what to expect next. It's not clear what we'd want to calibrate to. Another conclusion is that while these, you could argue these are statistically significant, again, you'd have to be a little more rigorous in your analysis to conclude that. But I just want to make the discrepancy between statistically significant and like the magnitude of the error. It's a discrepancy can be statistically significant and be sort of practically not that significant. And my favorite example of this in the real world is statistically, baby boys are more common than baby girls. The p-value would be astronomically low if you actually looked at the data from all the hospitals. Baby boys are about 50.1% of births, and I think baby girls are like 49.9%. I think that's about the level of discrepancy. But in practice, if you go about the world assuming that baby boys and baby girls are equally likely, you're not going to suffer too much from making that assumption, from being off by that little bit. So likewise here, there's fairly good evidence, I think, in totality that we're off by something, but I think the amount of it does not explain this very big discrepancy that we saw at the beginning with the overall model. So I suspect that the independence assumption is what's really causing some of that big miscalibration, where we said we should be right more than 70% of the time. We're actually only right 57% of the time. I suspect the independence assumption is playing a bigger role in that than any of the miscalibration we see here. But our next steps will be to further investigate approaches to calibrate and see also what we can do about this independence assumption, see if there's a way that we can do something better to model what the total number of runs scored is going to be given the individual predictions of the two separate teams. Anyway, I hope you enjoyed that video. I think we've got exciting things coming forward. I'd like to encourage you again to please like this video and subscribe to the channel so you can know every time a video comes out. And I look forward to seeing you in the next video. And if you'd like to, please join the Discord channel. I'll have the invite here. It'd be great to chat with folks over there. Have a great day.